Today's lesson is looking at the idea of Riemann sums and writing them into summation notation using a limit, and then looking at definite integral notation. So this is kind of like when we were first learning derivatives, and we had this limit definition of a derivative, and later we learned all these shortcuts, but we still want to recognize that limit definition of a derivative. So kind of similar idea to this lesson. So starting out, I just want you to think about finding the area under this curve. And let's just start with a one single rectangle. So I'll do like this left Riemann sum, and I'll go over. And there we go. That's not a perfect rectangle. That's better. And sure, that is an estimation. It's not great, but it would get us somewhat close. But now let's look. If I increase the amount of rectangles, you can tell right away I'm going to get a closer approximation. So now imagine putting an infinite number of rectangles under that curve. That would give you that area under the curve. Okay, so now I want you to maybe just pause the video and actually jot this graph down. And what we're going to think about is we're finding the area of this curve from A to B and with n subintervals. Now remember, we want to think about how do we find the width and the height of these rectangles. The width of every rectangle is that change in x. And how do you find that change in x with this information? So that change in x, we would basically subtract our endpoints, so the b minus a, and then you divide by how many rectangles you want. So doing that b minus a divided by n tells you the width of every rectangle. So now how do we find that height? Well, if you look at the very first point, that height was at y value, so our function f at a. And then this one is our function, and it's a plus one change of x. And then this one is f of a plus two changes of x. So I added another rectangle, moved that b over, so this one would be f of the original a plus 3 changes of x. So I'm going to write this as the height is f of that starting a plus, so 1, 2, 3, that constant times the change in x. But now, what is the change in x? We just wrote that here, so I'm going to input that f of a plus k times b minus a over n. And then how do you find the area? Is you're multiplying the width times the height. So the width, b minus a over n, times the height, which is f of this a plus, and I'm going to write this as b minus a over n times k. So there's this area, but we want the summation. So I don't know if you remember in pre-calc the summation notation. So what we're going to be doing is the limit as our subintervals approach infinity, and then we're looking at the summation of this area where k starts with 1 and we're going to n, where n approaches infinity. So this right here is our summation notation for finding area under a curve. Okay, so here is this limit summation notation of our Riemann sums. But who wants to work with this messy nonsense all the time? So we, of course, have created notation. This is the definite integral notation, where here's our s. So if it's from a to b, we're going to write this from a to b, and then of our function with respect to x. So these two things are actually communicating the same thing. This is kind of the meaning behind this, and then this is just to create an easier notation. And what we're practicing today is just switching back and forth between these two notations. Okay, so you don't have to rewrite this. I put it there as a reference. So our example is the integral from -1 to 3 of the function x squared. What we're going to do is take this simple notation and put it into this complicated notation. So the first part is going to be just this. The limit as n approaches infinity. The summation as k is 1 to n. Okay, so the b minus a, that comes from here to here, so our interval. And if we're going to do b minus a, 3 minus -1, that is 4. So this part here is just going to be 4 over n. And then this is function notation, which tells you to plug what's in parentheses into your x. So all of that is going to go into this x squared. So times, okay, the a value is the starting, that -1, plus the b minus a over n is the 4 over n, times k, so I'm plugging all of that in for x, so all of that is squared. So that is converting the definite integral notation into the summation notation. Let's do that one more time with one more example. So definite integral notation from -1 to 2 of the function e to x. So we got to write out the limit as n approaches infinity, summation, that's a silly summation, so k equals 1 to n. So this part, we just have to do b minus a, which in this case is 3. So 3 over n. And then I have to plug all of this into this function. So times e to the power of, and the exponent is where we plug all this in. So a is our starting, -1, plus this is the 3 over n times k. And that is it. Now we're going to go backwards, starting with the limit. So the limit as n approaches infinity. So if I have 8 over n, and then 4 parentheses, -1 plus 8 over n k. I can put 8k over n. So the first thing I notice is that b minus a over n is 8. So that means that I have to, b minus a would be 8. But what is a? What's my starting amount? And if you look here, this is that a. So a is -1, and if the difference is 8, it would have to go up to 7. Now technically there are multiple ways to interpret this. So these types of questions would be multiple choice questions on the AP exam. For the sake of the video, I'm just going to kind of pick the obvious one, and then in class we can look at some of the more possibilities, I guess. Okay, so what is this function? Well, if you remember, this is like what we're plugged in for x, and then I have this 4. So this is literally just 4x. And here is our final example, starting with the limit and it is 3 over n times -2 plus 3k over n to the power of 4. Turning this into the definite integral notation. So we know the difference from a to b has to be 3. Here is that starting amount a, so -2 to +1, and if this is what you're plugging in for x, and then we have to this 4th power, so it is x to the 4th power dx. So I'm going to say this again, there are multiple ways that really we can interpret these limit definitions into integrals. So going from the limit to the integral can be a little interesting. I'm just kind of picking the most obvious one, and then we can talk later about different possibilities. But there is your full lesson on the Riemann sums, summation notation, and definite integral notation. Good luck.